Hello, everyone. This is meteorologist and storm chaser Gabe Garfield, and today I'm going to be talking about advanced meteorology for storm chasers. Let's get right into it. So, what's ahead? Last time we talked about the forecasting approach and weather charts, including upper air, surface, and photograph. That's in the basic meteorology presentation that you can find on YouTube. Please give it a watch. And next, we'll be covering supercell ingredients, including instability, moisture, wind shear, and lift. And then we'll put it all together and how it all forms a supercell. Now, to start right off with supercell ingredients. So, today we're going to talk about supercell thunderstorms. These rotating thunderstorms are responsible for 70% of tornadoes, including practically all EF4 and EF5 type tornadoes, and also giant hail. So not every supercell is going to produce a tornado, but pretty much every tornado, 70% of them in this case, is produced by a supercell. So the approach here is that if we can learn something about how supercells form, the ingredients that it takes to produce them, then we can forecast tornadoes a little bit more reliably. So what do you need for tornadogenesis? Well, there are two ingredients, spin and stretch. Now, spin, meteorologists call this vorticity, basically just the tendency of air to circulate. And the second ingredient is stretch. So this is the idea of an ice skater pulling in her arms, and when she does, she spins faster and faster. So you need both of these for tornadoes to form. So a strong updraft is kind of like an ice skater as she brings her arms in and spins faster. So a strong updraft basically brings in that radius closer and closer together, and then the updraft, if it's already rotating, begins to spin faster. Now, supercells provide a reliable source for both spin and stretch. So, to reiterate, for supercells, you need instability, moisture, vertical wind shear, and lift. So, we'll cover each of these in detail. Steep lapse rates. A lapse rate is defined as the difference in temperature through a layer. Now, here we can see two levels, 3 kilometers and 6 kilometers. Now, at 3 kilometers, the temperature is 11°C, and at 6 kilometers, the temperature is minus 10°C. Now, a layer is the difference between two heights above ground. In this case, we have two heights, 3 kilometers above ground and 6 kilometers above ground. And so the layer here is the 3 to 6 kilometer layer. And the bigger the difference in temperature, the steeper the lapse rate. So you can think of it like the hot air balloon. The warmer the hot air balloon is relative to its surroundings, the faster it rises. And the steepest lapse rate above the surface is dry adiabatic. This is 9.8 Celsius per kilometer. Now, the closer to moist adiabatic, about 6.5 C per kilometer, the weaker the lapse rate. So the lapse rate will be generally between those two rates. In this case, we can calculate the lapse rate by noting the difference between the top level, 6 kilometers, and the bottom level, 3 kilometers. So this difference in temperature is 21 Celsius over 3 kilometers. So 21 Celsius divided by 3 kilometers is 7 Celsius per kilometer. So the lapse rate is 7 Celsius per kilometer. And this is actually the lapse rate that was seen on the Norman, Oklahoma sounding released at 7 p.m. on May 24th, 2011, during a violent tornado outbreak. Now you can see there where that is highlighted, the 3 to 6 kilometer layer. Now this view shows the difference between weak and steep lapse rates. So on the left, you can see an example from 2019 of a forecast sounding for an event in Kansas where the lapse rate was actually relatively weak. You can see here in the 3 to 6 kilometer layer, the lapse rate was 6.8 Celsius per kilometer. And this was near the town of Alta Vista, where there was a mothership supercell there. And on the right, you see the forecast sounding for the Pilger, Nebraska violent tornadic supercell, where the lapse rate was 8.3 Celsius per kilometer. And so you can see here that there's a pretty big difference in the lapse rate and a pretty big difference in the result. So obviously, the steeper the lapse rate, the more likely it is that you're going to get strong and even violent tornadoes. And you can see those layers here highlighted in the oval. Now, this is a big shout out to Cameron Nixon. He did provide these RAP proximity soundings, so appreciate that, Cameron. In terms of conditional instability, air is conditionally unstable if it will continue to rise above its level of free convection. So, in layman's terms, that means that the parcel temperature is going to be warmer than the environmental temperature all the way up through the top of the troposphere. Now, we do want to remember that the change in environmental temperature is the lapse rate. So you can see here that red line, that is the lapse rate that we're talking about. And the parcel temperature would be more like your hot air balloon temperature. And as long as that's to the right of the environmental temperature, remember temperature increases to the right in a skew T, then that air parcel is going to continue to rise unfettered. You can see the differences between these two lines highlighted in purple here. The bigger that difference is, the bigger the energy that the atmosphere has for updrafts. And the total area between these two is known as the convective available potential energy. We talked about that during the basic meteorology section. So if you're a little unfamiliar with that, that is something that I'd recommend you watch. So CAPE. CAPE is just the integration of total positive instability in joules per kilogram. And to make it as big as possible, you need a combination of steep lapse rates, high surface temperatures, and high dew point temperatures. So a few rules of thumb. This is nothing scientific, but something I found somewhat useful in the plains. In March, you generally want CAPE to be greater than 1,000 joules per kilogram for tornadoes. In April, greater than 2,000 joules per kilograms. And after May, anything above 2,500 is generally pretty good. So how do you get steep mid-level lapse rates? It all starts with westerly downslope flow. Let's take a look. So here's a diagram of the Rocky Mountains. We're moving from Albuquerque to Amarillo to Oklahoma City on the bottom as we're going from west to east, and then up is up. So let's imagine that we superimpose westerly flow over the mountains, pretty common case. So on the left side of the Rockies, the air goes up the mountain, which is known as upslope flow. And on the right side, it goes down. Now, if you've ever been to the Rockies, you know that the air at the top of the mountain is pretty light. That's why it takes a little bit of time to acclimate up there. It's less dense. And the air at the bottom of the mountain is more dense. So as the air follows the surface of the mountain, going over the mountain, that actually leads to more molecules hitting each other, which is a warming process. This is known as compressional warming. So that's the second step in this process. So now that you have the warm air at the base of the mountain, then you start thinking, okay, now we have a pretty significant difference in temperature between the top of the mountain and the bottom of the mountain. And this is where the formation of the elevated mixed layer takes place. Now, we need to talk about mixing. This figure shows how the mixed layer evolves during the day. So on the bottom left, you see this starts at noon and it ends at noon. So it's an entire 24-hour cycle. And then on the y-axis, you see height. So you can see from noon to sunset, the mixed layer goes up to the capping inversion, and the free troposphere is above that. Now, as time goes on past sunset, the air starts to stabilize near the surface, and you get a stable boundary layer through the middle of the night. And this is actually, incidentally, what explains why the low level jet increases after dark, because the mixing actually goes away after peak heating. And then that energy that was sort of equally mixed throughout the troposphere, the lower troposphere, is actually kind of concentrated just above the surface. So you get a stronger low level jet. And then the process repeats itself after sunrise the next day. So mixing is driven by surface heating. You can think of it like thermals, right? So you have hawks that fly really high during the afternoons on these thermals. It's the same concept. It's very important for convective initiation, it turns out. So if the height of the dryline circulation is higher than the level of free convection, there's a good chance you're going to initiate convection. It turns out that the height of the mixed layer west of the dry line is a good proxy for how deep the dry line circulation will be. And obviously, the higher that is, the greater the chances of convection. So here's a good example from 2012 from an outbreak of tornadoes. So this is a Lamont sounding. Lamont, Oklahoma, if you know about that, is in northern Oklahoma. And you can see that the LFC in this case is about 800 millibars. So you would be looking for, if you're looking at, say, sounding at Amarillo, you would be looking for a mixed layer that was at least 800 millibars tall, and you'd want it to ideally be taller for convective initiation chances. And here you can see the top of the mixed layer, actually at Amarillo, is 550 millibars. So that gives you a good sense of how the dryline circulation will evolve in terms of depth. So indeed, this day we did see storms fire all the way to Lamont's latitude. This works sometimes, and sometimes it doesn't work so well, but it's at least a good proxy for knowing when convective initiation might occur. Now, that elevated mixed layer that we were talking about, it is pushed eastward by the winds aloft and is advected, that means moved by the wind, over the moisture to the east. So this is why it's known as the elevated mixed layer. So now we have most of the process for the formation of steep lapse rates. The final step is the formation of the Lee trough. So we can see here the development of the elevated mixed layer. You have the warm air at the base of the layer and the cool air at the top. So steep lapse rates, right? And the wind carries that air off the ground and transports it or advects it, that's the meteorological term, over the moist layer to the east. That's why it is known as the elevated mixed layer. Now, this process can actually take days. So you should be able to tell pretty far in advance about the potential for instability. Now, again, warm air rises. And so because of that, air rushes in from around to fill that vacuum that's left by the rising air. And this leads to formation of a low pressure. And this is the Lee trough. So I wanted to go through a real world example of Lee troughing and compressional warming. So this is a 500 millibar chart from May 17th, 2013 at 7 a.m. Remember, for this analysis, we are looking for strong westerly flow over the mountains for compressional warming and the formation of a lee trough. And so the lee of the mountains is the east side of the mountains. In this case, that would be running from, say, eastern Wyoming through eastern New Mexico. And we'd be looking for a westerly component here. We do see that the winds are westerly, but they're on the lighter side. So in this case, we wouldn't expect to see a very strong compressional warming and therefore not a very strong lee trough. And indeed, there is no area at the surface where the pressure is less than 1,004 millibars. Now, going 12 hours into the future, you can see this trough over the western United States coming a little bit closer. Flow may be a little bit more westerly, particularly over the southern plains, the southern high plains there in Amarillo. You can see the 30 knot reading, and then you see another 35 knot in western South Dakota. So you can see that the flow is increasing a little bit. The direction is a little bit more westerly, so you might expect to see a little bit more downsloping and compressional warming, and then the formation of low pressure. And indeed, if you contour pressure less than 1,004 millibars, you do see a nice swath developing in just those areas. Now, going into the future, 7 a.m. Central Time, May 18th, 2013, you can see that this upper trough is starting to move into the area, but the flow, if you notice, particularly over the lee of the mountains, over eastern New Mexico, eastern Colorado, eastern Wyoming, it's a little bit more southerly in this case. So even though the flow is stronger, it's less westerly. So you might expect that because the component is not so westerly, that the compressional warming wouldn't be as strong, which means that you wouldn't get as much of a lee trough. And indeed, when you look at the surface at that time, you see that the pressure is less than 1,004 millibars. Um, and there may be some diurnal effects as well to mention there, but primary thing to mention is that the upper flow, if it's from the south, will not contribute as much to the formation of the lead trough and indeed the elevated mixed layer. You want to look for westerly flow. Now, by the evening on May 18th, 2013, May 19th at 0Z, you do see stronger flow. It is still pretty backed, but in general, it is westerly enough that you might expect to see some lee troughing. And indeed, we do see that here with a large area of low pressure. So that causes the air from the east to rush into that. Remember, air flows from high to low, and that's especially true near the surface. And you can start to see how that pulls in that vex, that higher dew point air. So you can see the 70s over North Texas, over you know, starting to edge into Oklahoma. Those are getting drawn into that low. And so it's pulling that moisture into Kansas where a significant event is about to take place. So you can see here the elevated mixed layer again. And one thing I want to point out is the air rushing into the low actually does draw in moisture. And you can see here at the 850 millibar chart showing winds just above the surface of the earth. You can see it bringing in that really rich, high octane Gulf moisture into the plains here. Mixing ratios 12, 14 grams per kilogram. So pretty good moisture coming in. And indeed, that's where the low level jet is. It's moving that moisture to the north. So this all culminated in a 3-day tornado outbreak. The charts ended on May 19th at 0Z, which was about the time that Roselle, Kansas, was nearly hit by an EF4 stovepipe tornado that you see at top left. And then the next day, I saw a tornado at Shawnee, Oklahoma. It was a half-mile wide, very violent tornado, very loud as well. And then the more Oklahoma EF5 that I saw on Monday that was very tragic and unfortunately did kill a number of people. It was the loudest tornado I've ever heard. That happened during this sequence as well. Moisture depth. Now, deep moisture prevents turbulent mixing. So we really do want that nice elevated mixed layer, those steep lapse rates that we've talked about. But often that is a double-edged sword because it also brings pretty dry desert southwest air, right? And if the convective mixing is strong enough, you'll mix some of that dry air down to the surface, and that will degrade the quality of the moist layer beneath it. So if you have higher moisture depth, this keeps instability high and mitigates downdraft strength. So a rule of thumb would be that you do need about 75 millibars for tornadoes, 75 millibars of depth, that is. And here is a forecast sounding from 2004 that shows kind of a minimum layer here that you would want to see for tornadoes. And indeed, this particular sounding produced this tornado that hit in central Illinois, just an absolute beast, F4 tornado. So it doesn't have to be super deep, but deep enough. Now, in terms of source regions of moisture, this is really important in the early season because the moisture is just hard to come by in the early season. So you really want to be on the game with this in the early part of the season. So even if there's southerly flow over the Gulf, you might not actually get quality moisture in the plains. And I'll show you why that's the case. Now, of course, later in the season, this doesn't really matter as much because the quality moisture is pretty likely late in the storm season, but that's when other supercell ingredients become more important. So in this case, this is from March of 2004, and what I want to point out is the trajectories of the return flow over the plains in this particular case. So if you look at this is another slow process, by the way. It does take days for this to occur. So if you're actually looking at a severe weather event 3-4 days from now, you might consider looking at observations over the Gulf if you're concerned that moisture will show up. You can actually see this play out and make good guesses as to whether or not you're going to get the moisture you need for storms. So in this case, you can see if you follow the trajectory from just east of the Florida Peninsula, it's going to follow those winds from northeast to southwest and then across the northern Gulf. And then as it gets to the western Gulf, it's going to turn to the north as southeasterly winds take it into the plains. So what you're seeing is essentially modified continental air that is being pulled into the plains. So that Gulf of Mexico moisture source is not going to be as effective here in bringing high moisture content into the plains. And you can really see this play out over several days before the severe weather event. By the way, that was on March 27th, 2004. So on March 24th in the evening, you can see that you continue with the northeasterly winds over the Florida peninsula and pretty good southerly flow over the plains, but we're bringing in, again, pretty modified continental air. And then as time goes on the evening of the 25th, same pattern. And then the winds start to turn a little bit on the 26th evening, and then a little bit better by the time of the event on March 27th. You can see the supercells in western Oklahoma, but the dew point temperature is actually in the low 60s here. So pretty decent for March, but not quite high enough to produce a major tornado outbreak, because even though the kinematics, the wind shear was sufficient for a major tornado outbreak, I actually chased this day. It turns out the moisture but just wasn't there. And you could actually tell this from the weather charts several days in advance. So something to keep in mind as you're forecasting. Now, I wanted to get into the effects of inland mixing. Now here I've plotted the 65-degree Fahrenheit isodrosotherm, so line of constant dew point, and this is from the morning of March 26th, and 24 hours later, what do you notice? It's in the same spot, right? So even though 24 hours has passed and we have winds from the southeast supposedly moving or advecting moisture to the north over the plains, this 65-degree line hasn't moved. So why is that? And I think the answer can be found in the observed soundings. So at Corpus Christi, you can see that there's pretty good moisture depth and pretty good dew point temperature. Dew point temperature here is almost 20 Celsius, which is about 68 degrees Fahrenheit. So very high moisture content in terms of magnitude. The depth looks at least 100 millibars. So everything is A-OK with this particular sounding. You go to the north, though, you do see some problems at Fort Worth, which is in North Texas. And you can see shallower moisture. And the dew point temperature here is about 16 Celsius, which so it's a little lower. But more importantly, you do see this dry air that's just above the surface, maybe some subsidence going on here. So that's going to be potentially problematic for the return of moisture. So the sounding at Fort Worth the next morning, the first thing I want to draw your attention to is the moisture depth. You see that that is increased by quite some millibars here. And you'll also notice that the dew point temperature is about the same as where it was, about 16 Celsius. So it seems that the moisture depth in this case had increased, but the magnitude of the moisture stayed the same. Now, some of that dry air was getting eroded, but it didn't seem like it was going to be in time for that event. And you can see the dry air here. It's a little less than what it was, but it's still problematic for moisture return in the plains. So sometimes moisture can arrive just in time for a severe weather event. I can think of one in particular, April 10th, 1979, the date of the Red River Valley outbreak. That was the date of the Wichita Falls, Texas monster F4 tornado that lasted for over an hour. I think it was up to 2 miles wide. Well, the moisture that day arrived just in time for that event. So, what are some events that you can think of where the moisture came in just in time for tornadoes? Feel free to comment and we can talk about that there. Now, on to vertical wind shear. Vertical shear is what organizes storms. So, if you don't have vertical wind shear and you have instability and moisture and lift, you'll just get ordinary thunderstorms that go up and that go down, and maybe they'll produce a little hail, maybe some lightning, but generally speaking, aren't a great threat to life and property. But it's actually vertical shear that actually organizes the thunderstorms into a configuration that produces major severe weather. Now, we can look at a vertical wind shear profile here where we basically have wind that is increasing with height. So those blue vectors there show that the wind near the surface is not as strong as the wind above it, and they're both pointing in the same direction. And you can imagine if you put a paddle wheel in the center of that, paddle wheel is going to rotate about that orange line, and that is essentially vorticity. We'll talk about that here in a minute. But if you superimpose an updraft into the middle of that, you actually get vertically oriented circulations. So in this case, the vertical circulations are oriented in two different directions. You have a rotation that's oriented clockwise on the north side of the updraft, and then one that's going counterclockwise on the southern side of the updraft. And if the wind profile is particularly favorable, you would actually see the southern one being preferred. This is known as the right mover, and the one on the north side is known as the left mover. And let's say that there's a case where it is a pretty favorable situation for the right mover. That would then mean that the storm would actually be favored. And then if you can imagine that the air that goes up has to come down as a rainy downdraft, it goes down and then it's pulled around the circulation in a pretty familiar shape, aka the hook echo. Now onto the concept of bulk shear. Bulk shear is used to approximate the shear through the depth of the storm layer. So 0 to 6 kilometers is the standard layer, and it assumes that all shear in that layer is available, which may not always be the case. That's why sometimes you'll see folks using effective layer shear because it's basically what the storm can effectively use. But in this case, bulk shear will be good enough for us. The rule of thumb is that greater than 30 knots is what you need for supercells or storm organization. So you can see in this particular image on the right, this is from April 14th, 2012. Big tornado outbreak across the plains. You do see bulk shear well above 30 knots, in some cases even 70 knots. So that's what you call strong or even very strong bulk shear. And this actually leads to mid-level rotation, which is actually pretty important. In this case, you can see an example from May 29th, 2008. This is a long track supercell on a high risk day in northern Kansas and Nebraska. And this was actually producing a long track tornado near Jewel, Kansas. And what's important about this is that the rotation in this case was offsetting the cooling of the surface that was taking place. This is actually from about, I think, about 10 p.m. that night. So the surface layer had already cooled and the cape had already lowered and the cap had already increased. But because the rotation was so strong in the supercell, it actually kept the updraft near the surface of the ground, moving right into this thunderstorm in a way that could keep the storm going. So basically, the supercell, the rotation acted like a big vacuum cleaner and kept lifting parcels in spite of the thermodynamic tendency otherwise. So that's why mid-level rotation is important. The weakness of bulk shear, again, it only measures the magnitude of the shear. It does not consider the direction of the shear, which can be important. And for this, we actually do need to dig into the hodograph. Now, to start out the hodograph, we want to consider relative motion. So in this case, I have the example of a car that's moving to the right with, a vector of 30 miles per hour. And let's say that there's a car that's passing that car going 50 miles per hour. Maybe it's a Corvette or something. Well, the relative motion, that is, if you were in the 30 mile per hour car, you'd actually almost feel like you were moving in reverse, or that maybe that the red car was moving at 20 miles per hour while you're stationary. That's what relative motion actually means. So we can apply that to the hodograph. And if you haven't actually looked at the photograph before, I'd really encourage you to look at the basic meteorology video that I've already posted. This really goes into depth about how you construct a photograph, and it's really important to understanding this piece and the pieces subsequent to it. So the storm relative wind can be found by drawing the vector from the right mover's motion to the photograph. And you can see where I've labeled the right mover motion as R here. And so basically you take a vector, the tail of a vector at the R location, and then move it towards the photograph. And you'll see that here with this green vector moving to the surface. That's the storm relative motion at the surface. And at 1 kilometer, and at 3 kilometers, and at 5 kilometers, and at 6 kilometers. Now, the area bounded by the hodograph and the storm relative winds at the top and bottom of the layer is known as the storm relative helicity. So this really just shows how much tendency for spin there is. And you can see that area, in this case, from surface to 3 kilometers, is this. That's a 0 to 3 kilometer storm relative helicity. Now, for tornadoes, I would say it's even more important to look at the 0 to 1 kilometer layer. So if you looked at that, that would be this. This little triangle is the 0 to 1 kilometer storm relative helicity. Now, that's 0 to 1 kilometer helicity is also known as low level shear. It's used primarily for tornado potential. So some rules of thumb, these are just what I've used. I think there's some studies to back this up. I didn't go into great depth to understand exactly what those numbers are, and I think they vary from location to location and from time of year. But some rules of thumb, generally above 100 meters squared per second squared is good for tornadoes, 200 for strong tornadoes, and 300 for violent tornadoes. Now, streamwise vorticity and storm structure. So we talked about this particular vertical shear orientation with that orange line being the axis of spin. This is also essentially the orientation of the vorticity vector. So that's basically, if you think about the right-hand rule, that would be like your thumb in pointing along that axis. We'll talk about that here in a second. So there's the vorticity vector. Now the right-hand rule. So the right-hand rule is your thumb, all your fingers point in the direction of the shear vector, in this case, the direction of the hodograph. And then your vorticity vector is to the left of that. And you can see this on the hodograph. By the way, the vorticity vector length is proportional to shear magnitude. So the stronger the shear, the longer the vorticity vector. And you can see that here in this particular demonstration. You can see, by the way, if you look from 5 to 6 kilometers, you can see that the length of the shear vector is shorter. So that's why I depicted the arrow to be shorter for the vorticity vector. So you can see the effect of shear magnitude on vorticity. Now, let's say you have all of those vorticity vectors. Now, the component of vorticity vector that is parallel to the storm relative wind is considered streamwise. So that's a mouthful. But basically, let's plot the the storm relative wind. And if that storm relative wind is going in the same direction as if the storm relative wind is going in the same direction as the vorticity vectors, then that is considered streamwise. So you can see at the surface, pretty streamwise, not so streamwise at 1 kilometer, but more streamwise as you start getting up to 3 kilometers, 5 kilometers, and so on. So that's actually really important. The more streamwise your vorticity, the better it is for tornadoes. So we talked about streamwise vorticity. Here's just another way of looking at it. Again, storm relative wind is flowing essentially parallel to the vorticity vector. Now, if it's opposite of that, when it's opposite, that is actually known as crosswise vorticity. So it's orthogonal to the vorticity vector and is parallel to the shear vector. So this is not good for tornadoes. You don't want to see that. So I wanted to look at some real events and their forecast soundings. Here is one from 2014. This is associated with the Pilger, Nebraska violent tornadic supercell. And if you look at this pretty carefully, you'll notice that there's very streamwise vorticity in the lowest 3 kilometers. So if you take that bright moving motion here, and then you trace it back to the hodograph to get the storm relative flow, you'll notice that if you also look at the vorticity vector, which is to the left of the shear vector, so in this case, by the way, the shear vector is essentially the hodograph itself. So the hodograph going this way. So that's the direction of your fingers. And then your thumb would be pointed to the left of that. That's the direction of your vorticity vector off to the left. Your storm relative flow is actually parallel to that vorticity vector. And that's true pretty much through the lowest, say, 2 or 3 kilometers. So it's very, very streamwise in the lowest 3 kilometers. And indeed, actually, it's pretty streamwise as you go up as well. So that's obviously very good for tornadoes. This is the event as it happened. Double wedges, pretty infamous event here. Both tornadoes were rated EF4. Now, this particular forecast sounding is from 2017, associated with the McLean, Texas tornadic supercell. And you'll notice that it is very streamwise in the lowest 500 meters. So you can see here's the right moving motion off to the northeast at about 37 knots. And if you follow the storm relative wind to the hodograph, it goes off in this direction off to the left. And then if you think about the hodograph as being your shear vector, you can see that if you point your fingers in the direction of the shear vector, your thumb will be pointing to the left again. So this is streamwise vorticity as your vorticity vector, and your storm relative flow are in the same direction. And that's true primarily through the first, say, half kilometer of this forecast sounding. But you'll notice that once you get up to 2 and 3 kilometers, it's not so streamwise, particularly at 1 kilometer. The angle really starts to change to something that's a little bit more crosswise. And then it becomes a little bit more streamwise with height, but not nearly as good as it is in the first half kilometer of the troposphere. But it turns out that the most important level for streamwise vorticity as far as tornadoes is concerned is actually in the lowest, say, kilometer, maybe even 500 meters. So indeed, this storm produced a tornado out there in the eastern Texas panhandle. And so definitely you can have that sort of veer back veer type of wind profile and still see tornadoes. So that's something that's not necessarily bad if you're looking for tornadoes. So Cameron Nixon and his colleagues have done an incredible job to tie the shape of the hodograph to storm behavior and structure. And I'm not going to share all of that work with you, but I want to highlight 2 key concepts from that work. The first is low-level storm relative wind and its relationship to storm size. And the second is upper-level storm relative wind and the precipitation pattern. So if you have weak storm relative winds in the lowest levels, this actually leads to smaller storms or mini supercells. You can see that here in this particular example hodograph, actually really just looking at the shear vector in the lowest kilometer. You can see that the right moving storm motion is to the northeast, and then the distance between the right mover and the hodograph is actually relatively small. So that's a relatively small storm relative wind at 1 kilometer and also at the surface. And so what you can infer from that is that you're not going to get as much mass moving into supercell thunderstorm. And so therefore the storm is going to be on the smaller side. Now there's a bit of complexity to this. It's not just as simple as a mass flux relationship, because if you do have mass going into the bottom of the storm, it's also going to come up the top of the storm and is going to affect the outflow at the top of the storm, which is then going to affect the storm relative winds. But just to keep it relatively simple, we can say that the strength of the storm relative wind at the low level is tied to the size of the storm. In this case, weak storm relative wind means smaller storm. Now, the converse is true. If you have strong storm relative winds in the lowest levels, you do get large supercells. So you can see here kind of a similar-ish right moving storm motion, but the shear vector is a bit further away. So you actually do get a very strong low-level storm relative wind at the kind of in the inflow layer, which leads to the development of large supercells. And the second concept is related to the outflow structure of a hodograph. So we're going to be focusing in this particular part on the upper part of a traditional hodograph, really the mid levels. So if you have weak storm relative wind in the mid to highest levels, you get high precipitation supercells. So you can kind of see that here. The 3 to say 6 kilometer layer, you can see the storm motion is to the east southeast, and if you plot a storm relative wind relative to that to those shear vectors, it actually is pretty small. So basically, the storm is moving right into its outflow, it's into its range, so it's kind of choking it off, and so you do get these kind of HP supercells. Now, I shouldn't say choking it off because that would imply the storm is not as strong. It is often the case that you do see large, nasty tornadoes with HP supercells, but this would not be particularly visible. You wouldn't see the classic or LP supercell structure with this. Now, and the converse would be true. So if you have strong storm relative wind in the highest levels, that would actually lead to classic, maybe even low precipitation supercells. So that sort of anorexic looking supercell where you can really see the rotation and the updraft, and it's very pretty, very photogenic. That happens in the cases where your storm relative wind is actually fairly strong in the upper part of the hodograph. So next we'll talk about outflow boundaries and their relationship to enhanced low-level shear. So outflow boundaries are a source for enhanced low-level shear, and we'll discuss how that works. But generally, outflow boundaries are boundaries that are created by evaporating rain. So you get evaporation, which is a cooling process that creates cooler, more dense air, and that spreads out from the storm. And then at some point, that stalls. Hopefully, it stalls in the case where you want tornadoes, and then it begins to. In the best cases where you have tornadoes, it begins to sort of warm or cook under the sun, and it doesn't undercut your storm. And so those are the type of boundaries we look for when we're interested in knowing where a tornado might form. So here's a schematic of an outflow boundary where you have cool outflow on the left and sort of warm, moist air on the right, the warm sector. So you might think that the left side would be to the north and the right side would be to the south. And you can see the cool outflow because it is more dense, it sinks, and then it spreads out and then it moves towards the warm sector. Now, when it encounters the warm sector, it pushes up air, as you can see on the right-hand side, and then that kind of forms this rotor, this sort of horizontal circulation, which is very reminiscent to the piece where we talked about the increasing wind speed with height, creating those horizontal rolls in the atmosphere. Here's an example of an outflow boundary from 2016 that actually ended up producing quite an event. Some of you will recognize this. You can see it stretching from southeast Colorado to southwest Kansas to south central Kansas and on into Missouri. And this is at 7 a.m. Central Time. So what you notice here is that the temps on the north side of the boundary are pretty cool. So in the mid 60s with 60s dew points. So not terribly cold, but definitely something that you would need some modification for that to produce later in the day. To the south, you do see dew points in the upper 60s to low 70s, so definitely some juice there. So this would be kind of a favorable situation for that return flow, kind of modifying that cool outflow boundary and also keeping the shear on the outflow boundary. So it's got a Goldilocks type of situation where you want a little bit of shear, a little bit of outflow, but you don't want so much outflow that you undercut your storms, or you basically have too little cape to form very vigorous updrafts. So you can see here in the satellite image that the entire area over the southern plains was pretty much baking under the sun. You can see no high cirrus, only just a few low level clouds. And you can even infer a pretty strong boundary position here from western Oklahoma on up into southwestern Kansas. And then you can see some horizontal convective rolls. This is at 1:45 p.m. So what this would suggest is, if you recall from our low-level lapse rate conversation, that this hasn't quite destabilized fully yet. But because of the sun, it's only 1:45. You'd expect that that would continue, and you'd also take advantage of your shear. And indeed, by that time, you can see that there's some modification of the temperatures there on the north side of the boundary, upper 70s, even to low 80s in southern Kansas, with dew points in the upper 60s. This is something that, as a storm chaser, your eyes definitely light up when you see something like this and say, "Okay, I know where I need to go. I need to go to the boundary." And indeed, that day, just on the north side of the boundary near Dodge City, this is the famous Dodge City machine, the tornado machine that produced more than 12 tornadoes near that town. And there were other tornadoes as well, including some pretty strong tornadoes. Now, the final section that we're going to be talking about is lift. And this is the final ingredient. This is important because with all those other things put together, if you don't have lift, you don't get a storm. And if you don't have a storm, you don't get a tornado. So this is a very key ingredient. Now, I wanted to talk about the different scales of lift. So we're going to talk about large scale lift and mesoscale lift primarily in these next sections. So large scale lift, you can think of the velocity as, in the upward direction. You're really talking at about a centimeter per second. So really kind of slow motion when you're talking about vertical velocities. The categories of lift sources for large scale lift would include quasi-geostrophic vertical motion, ageostrophic curvature divergence, and you can talk about straight jet theory. So we'll talk about all of these in detail here in a minute, but those would be categorized under large scale lift. Now, mesoscale lift is actually 2 orders of magnitude larger than large scale lift, which is why it's quite a bit more important when you're thinking about convective initiation for the development of storms. So that's about 1 meter per second on average. So you can think about this in terms of like a dry line circulation. That's a form of mesoscale lift or a boundary intersection. And for storm chasers, we know that dry lines are typically, particularly in the southern plains, a really good place to find supercells and tornadoes. And then you do have storm scale lift, which actually is an order of magnitude larger than that at 10 meters per second on average. So you're looking for more in terms of like thunderstorm outflow boundaries that cause other storms to develop. That would be storm scale lift, a little less predictable. So we won't really talk about that here, but just so you know, these are the motions, relative motions associated with these forms of lift. And moving on to large scale ascent first, we'll start with quasi-geostrophic theory. So remember that the Coriolis force balances the pressure gradient force. So the Coriolis force goes to the right of the wind, and the pressure gradient force goes to the left in the northern hemisphere. The resulting wind from this balance is called the geostrophic wind, and the geostrophic wind flows parallel to the isohyets. Above the friction layer, though, the winds are generally or quasi-geostrophic. And so you can see here that the winds indeed seem to follow these black isohyet lines. So that's checking. You'll notice that over here, that seems to fall apart a little bit as we do see this wind pointing to the north across an isohyet line. This would be an example of an ageostrophic wind or a strong ageostrophic component. And that's usually found where you have highs and lows that are particularly strong. So there's a strong ageostrophic component. And usually where you see that, there's also strong or reasonably strong temperature advection or movement as well. So the quasi-geostrophic vertical motion equation. I won't show you all the math. It is very gory in its details, but suffice it to say, basically the equation says that the vertical motion is equal to the change in vorticity advection with height, that's term one, plus the temperature advection, and that's term two. So we'll dig into the first term here now. So you can imagine that if we're going up with height here, and we have vorticity that is stronger. So basically, remember that vorticity is the tendency of air to spin. So if the vorticity higher up in the atmosphere is higher or stronger than it is lower in the atmosphere, and they're being carried by the same level of wind, so basically no change in wind speed or direction, you're actually going to get the tendency for air to rise out ahead of that. And that's a mouthful, but basically you want increasing vorticity with height, and it's being pushed by the wind in a particular direction, in this case from left to right. And out ahead of that, if you have this configuration, you're going to see rising motion. So let's take a real world example and examine this for term one. So this is a 500 millibar chart from April 27th, 2011 in the morning. And the first thing you'll notice is a very large pronounced trough in the center of the United States and a very strong jet streak that I have contoured here in the blue and purple. And in the center of that jet core, which is roughly over North Texas, the winds there were greater than 80 knots, which is very, very powerful for any time of year. And what we're trying to do here is infer vertical motion from term one, which it talks about vorticity increasing with height and then being pushed by the wind. So our first order of business is going to be to identify where that vorticity might exist on this map. And so vorticity is composed of two things. So you've got the shear vorticity. So that would refer to the change in wind speed over a given distance, a shearing effect, and curvature vorticity, which is basically just the kind of traditional sense of spin. And if you're looking for those on this map near that trough, you would probably assume that if you go to the base of a trough, you'll find pretty strong vorticity there. There's very good curvature here, so that would add a component of vorticity. And then there's a little bit of shear. If you put a paddle wheel, imaginary paddle wheel right here through the southern plains, this wind would push the southern part of the paddle wheel out this way while the northern part would sort of drift, and so that would create this sort of cyclonic spin on the north side of the jet. So both the curvature and the shear are there, and so that's where the vorticity would be strongest. So now that we know where the vorticity is, what we can do here is just assume that in general that the wind speeds do increase with height, and that's something that you would maybe understand from a thermal wind relationship. We won't get into that so much here, but basically the winds increase generally speaking, with height. And so the vorticity thus increases with height as well. So you get that differential part. You've got the vorticity, and then you've got the winds that are pushing that along. So you have the advection. So what you would imagine is that anywhere essentially downstream of that vorticity at 500 millibars is where we're going to get differential positive vorticity advection, which means rising motion. And just to show this out, here is the analyzed vorticity from that same time. And you can see exactly where that is, just to the north side of the jet streak at the base of the trough, which is where you generally see it. And the rising motion would be out ahead of that, where that advection or that vorticity is being advected. So it's being pushed by the winds following these height contours towards northern Arkansas, southern Missouri, and places to the north and east. Now, identifying vorticity maxima. The best way you can do this, besides looking at obviously 500 millibar charts, is you can look at water vapor imagery, and really anytime you see sort of these drier colors. So this would be these oranges, and sometimes browns. That's where air is subsiding or sinking, so it's going to be a little bit drier. And then you've got the more moist air off to the east. So basically, anytime you see an interface there, that's where you have rising motion, and you can see the essentially the vorticity maxima associated with this particular jet streak right here. Maybe you've got some warm air advection going on here over the southeast. And so that would be, I guess, where I would identify that particular vorticity maxima. Now, warm air advection was a little bit harder to define here, but this is the second term again of the vertical motion equation from quasi-geostrophic theory. And essentially, anywhere where you see those reds, there's pretty good warm air advection. So you can spot that in northern Alabama and northern Mississippi and into southern Tennessee. And so that's another large scale forcing for convection. And another way to infer warm air advection, this is from Jackson, Mississippi, and so you can see this in action. Anytime you see winds that turn clockwise in direction as you go up in height, that is warm air advection. So since you do see that clockwise turning with height, that you can infer there's rising motion there from the warm air advection term of the quasi-geostrophic vertical motion equation. Incidentally, it also kind of carves out this nice photograph that is also associated with tornadoes. So that seems to go together. No coincidence there. And again, that's the clockwise curvature that I was just talking about. Another large scale lift factor is called ageostrophic curvature divergence. And that is a mouthful. So I won't get into all the reasoning behind this, but suffice it to say, what you generally see as a pattern is that the divergence is strongest with this particular cause for lift. So divergence, meaning separations of winds, that's strongest in advance of trough. So this would be like basically the axis of the trough out ahead of that. And before you get to the ridge, so kind of in between, that's where you're going to get your divergence and your strongest rising motion from this particular factor. And then on the converse, behind the trough, you tend to get more convergence. So you can see that would be not favorable for rising motion. And so why divergence is important. So divergence means just air that's parting or separating, going in different directions. And usually, obviously you have to increasing wind speeds as well, is because once the air is diverging at the top of the atmosphere, it has to be filled by something below it, which creates sort of this convergence below it and cause for rising motion and storms and that sort of thing. So that's where you would expect to see the storms. And in this particular view, here's a 250 millibars. We typically look for this at the highest levels of the atmosphere, kind of near the tropopause. And you can see here the trough coming in, the negative tilt, and kind of the area between the trough and sort of this ridgy features. You might expect a little bit of ageostrophic curvature divergence happening in these areas. And the final piece that I'll go into is associated with straight jet theory. So straight jet theory says if you take a straight jet, so no curvature, just looking at a straight jet, you'll get this kind of pattern where if the jet is moving from, in this case, west to east, out ahead of it to on the left front quad as it's moving in this direction, left front quadrant here, you'll have divergence. The right front quadrant, you'll have convergence. And then the opposite is true when you get to the left side of the jet. So you have convergence in the left rear quad. So that would lead to sinking motion, and divergence in the right rear quad, which would lead to rising motion. So essentially, where you see the divergence, that's going to lead to rising motion. And so if you look at this particular map, it's a little tough to tell because there's nothing straight about this particular situation, but you can kind of identify a little bit of a jet streak here over West Texas and maybe one that's kind of exiting over, say, Northeast Arkansas into Illinois. So if you apply that theory, so the left front quad of this entering jet and the right rear quad of this exiting jet are the areas of rising motion or divergence. You'd expect to see rising motion there and there. And so when you put it all together, all the sources of rising motion, you can see, generally speaking, that you're going to get pretty strong rising motion over the southeast United States. And so when you look at this low pressure system at the surface, that was located basically over eastern Oklahoma and western Arkansas, based upon where this was and all these combined together, you would imagine that essentially the low would move kind of maybe in east or even northeasterly direction. And this is the evolution of that. This is at 7 in the morning to start with. Again, eastern Oklahoma, western Arkansas. And with that lift being kind of focused out in these areas, you'd kind of expect that that low would track generally in the direction of northeast Arkansas. And so let's see what happens. Indeed, you can see it moving into north and northeast Arkansas here. And the final topic of ascent is mesoscale ascent. So let's get into it. The dryline circulation. This is from a paper by Shui and Martin in 2006. So basically, this talks about some various details about how convective initiation occurs. You typically see sort of this western dryline where it's essentially your primary dry line. And then you kind of have this dry line transition zone between, say, western dry line and the eastern dry line. And in between, you have what are called horizontal convective rolls. I won't get into exactly what they are, but the point being is that this horizontal convective rolls are where you see enhanced convergence and kind of get a bend in the dry line. This is where it's most likely that you're going to see convective initiation. And so be looking for these on satellite. If you see these, particularly on the eastern dry line, that might be an area to focus your eyes on as you're looking for where storms might develop. And another possible area to look at would be, say, boundary intersection. Here's one from the infamous May 31st, 2013 El Reno event. You can see this sort of stalled boundary from southwestern Oklahoma all the way up to northern Oklahoma. And then you have a dry line intersection just west of Oklahoma City. And that was an area of enhanced lift where all of that air is kind of put together. And since it cannot go into the ground, it has to go up. And so it's essentially forced up. So that would be another source for lift to think about. And you can see here in that case, that's where that area of enhanced lift was on May 31st. And then it exploded right on that boundary. And you can see also the boundary was, kind of a source for lift all the way up into Missouri. So it wasn't just at that stalled intersection with the dry line, but it definitely helped in that case. So putting it all together. So here's the situation that was the case on May 31st, 2013. So you had this jet stream that was diving from the Pacific Northwest to the southern plains, and you had the moisture that was over the Gulf of Mexico ready to be drawn up into the plains. And so, how did that happen? So, if you take a slice through the atmosphere, say from around Denver to Oklahoma City, and what you would see is what we've talked about already. So, westerly flow moving over the mountains. As it moves over the mountains, it follows the terrain and it moves down slope. That's a warming process. The warming air then rises, leaving a wake of low pressure. And that low pressure is the lee trough. And that lee trough enhances the return flow of moisture from the Gulf of Mexico. So the low level jet, surface winds kind of turning in to the low pressure, bringing that moisture into the southern plains. And so then you can see this on the actual map here, and you can see that moisture moving into the plains. And at the same time, we're bringing the elevated mixed layer, right? The warm air just above the surface and then decreasing with height, those steep lapse rates moving in from the west. And that intersection of the warm, moist air beneath and the dry air above that decreases in temperature pretty rapidly, creates a zone of unstable air over the plains in this case. And so then at the same time, so you have the thermodynamic setup, you've got your moisture, you've got your instability, and now you've got your wind shear. In this case, we've talked about this. This is a straight shear. Obviously, there was some curvature in the case of El Reno, but just for argument's sake here, you put an updraft in that. You get counter-rotating vortices, right? In the case of better wind shear profiles, which are more clockwise turning with height, you actually do favor that southern updraft. And then you form
a rotating updraft on the southern side that's stronger than the northern side, and so that grows and expands into a supercell thunderstorm. The rainy downdraft is separated from the updraft, and the precipitation is wrapped around the updraft in a hook echo. So if you put it all together, you get this supercell thunderstorm. And again, from the supercell, you form 70% of tornadoes. So this increases your odds of seeing a tornado, and that all comes from those four ingredients. So with that, I'll end there. And thank you very much for watching. If you would do me a favor, if you liked this video, please like and subscribe. We'll see you next time. Thanks.